Okay, so let's start talking about, let me make sure my microphone's on. Yeah, let's start talking about 1 through 15 odd and number 18 on 359. So if we have this function, it asks us to find the absolute min, absolute max, local min, and local max. What we're going to do is our process for finding the local, and then we'll do extrema at the end. So remember, for local mins and maxes, we say that step 1 is to find the critical values. Step 2 is to partition. And step 3 is to chart. And we just need to make sure when we're on these closed intervals that when we partition and chart, we include our endpoints. That is a small, subtle point that we need to remember. If we're just doing it in general, we don't have to worry about it. And then for the absolute mins and maxes, remember, step 1 is going to be to find our critical values. Yes, we've already done that. Step 3 is going to be to find the f of our critical values, f of our endpoints, and then step 3 is going to be to compare what we have in step 2. Okay? So again, local min and maxes is critical values, partition, and chart. Absolute is critical values, find f of the critical values, f of the endpoints, and then compare. So I'll move that out of the way so we have more room. And so now if we have this function, and we would, so if our original function is f of x is equal to x cubed minus 9x squared plus 24x minus 2 on the interval from 0 to 5, then step 1, if we want to find the local and absolute extrema, is to find our critical values. And every time I write down, it's where the derivative equals 0 or undefined. So we take the derivative and we find out it's this because it's a nice polynomial. Then we want to try and factor that sucker. So first, when you see this, you can pull out a 3. And then in here, it factors into x minus 4 and x minus 2. So where does the derivative equal 0? Well, I just set it equal to 0 and find out that one of the factors must be 0 to multiply together to get 0. So either 3 is 0, which doesn't happen, x minus 4 is 0, which gives you a critical value of 4, or x equals 2, which gives you a critical value of 2. Notice both of these are inside the interval, so they are actual critical values for this conversation. Then we partition the interval. Again, we use either the critical values or where the function doesn't exist. So here are the two critical values, but then because we are on a closed interval, we also want to go ahead and make sure that we block off our interval at 0 and 5. We don't want to test everything. We just have these 3 intervals. So now when I chart, my first interval is from 0 to 2. My next interval is from 2 to 4. My last interval is from 4 to 5. Okay? So I take any point inside 0 to 2, and I'm not going to take negative 100. If I take 0 to 2, so from 0 to 2, maybe I pick something nice like 1, and you see that 1 minus 4 is going to be negative. And then if I plug in 1, I get 1 minus 2 is also going to be a negative. So a negative times a negative is a positive. So my function is increasing inside of this interval. Now, I try the number 3 because it's in the interval from 2 to 4. I see that 3 minus 4 is negative. 3 minus 2 inside of this piece is positive. So a negative times a positive is negative. So the function is decreasing in this interval. Lastly, I try x is equal to maybe what, 4.5. So 4.5 minus 4 and 4.5 minus 2 both turn out to be positive. So a positive times a positive is positive. So if our derivative is positive, our original function is increasing. So now when we read this chart, if we're looking for a local min or max, we look where the derivative changes sign. So since our derivative changes sign from positive to negative at x is equal to 2, I can say that derivative changes sign positive negative at x equals 2 means that we have a local max. And how do you remember which is which? Just draw the picture. It goes from increasing to decreasing. That's a local max. Here we have the derivative changes sign from negative to positive at 4, right? So since it changes negative to positive at x equals 4, derivative negative to derivative positive means I have a local minimum. So I have found the two local extreme values. Now, remember, for absolute min and max, step 1 is to find the critical values, which we've done. Step 2 is to take f, the original function of the critical values, and f of the endpoints. And then step 3 is to compare the values you get in step 2. So first I take f of 0, and I get negative 2 if you plug in 0 into the original function. F of 2, if you plug in 2 into the original function, you will get 18. If you plug in 4 into the original function, after a little bit of work, you'll see you get 14. And then f of 5, you end up getting 18. Just to be clear, how can we do some of these without a calculator thinking, well, the 0 is easy because everything's zeroed out except the negative 2. But then for something like 2, just do it one term at a time. 2 cubed is 8. 2 squared is 4 times 9 is 36. And then 24 times 2 is 48. So then I just, minus 2, then I just grabbed these two and said, look, 48 minus 2 is 46. But 46 minus 36 gave me negative 10. With the 8, gave me 18. Now, f of 4 turned out to be 14, and f of 5 is 18. So when I look at all these values, the largest I got out when I plugged into my original function, when I plugged in the endpoints and the critical values, the largest I got out was 18. So my absolute max is 18. It occurs at 2 and 5. The smallest value I got out was negative 2. So that means my absolute min is negative 2, and it occurs at 0. We'll be right back to do more problems.